there, it's Shannon Matchick-Myers, and today we are continuing section 3.1 from the Zell text with our last example of applications that can be modeled using linear differential equations. So this one involves air resistance. In section 1.3, we saw that a differential equation describing the velocity of a falling mass subject to air resistance proportional to the instantaneous velocity is m times dv dt equals m times g minus k times v, where k is greater than 0 and is a constant of proportionality. The positive direction is downward in these cases. So solve the equation subject to the initial condition that v at 0 equals v sub 0. All right, so let's see what we have. For this first part, we have m times dv dt equals m times g minus k times v. Now this is not linear in form, right? So we need to get the term that has the v with it on the left side. So we'll add k times v, it's equal to m times g, and then if we multiply both sides by 1 over m, we'll have the correct format. So dv dt plus k over m times v is equal to g. Good so far? All right, so we need to find our integrating factor. So the integrating factor, once you have this in the right format, is the coefficient to the v term. So we have e to the integral of k over m, which I got from right here, with respect to t. And that is just equal to e to the k over m times t. So now, multiplying both sides by our integrating factor, we'll have, on the left, as was our evil plan, we'll have e to the k over m times t times v, and that's equal to g e to the k over m times t. Good so far? Now, I'll go back to the blue, sorry. So now, getting this in the form for integration, we'll have e to the k over m times t dv on the left is equal to ge to the k over m times t dt on the right. And now we need a factor of k over m dt in order to integrate the exponential term. And so to balance it out, we'll multiply the outside by m over k. And then integrating both sides, we will have, don't forget that that g gets treated as a constant as well because we're integrating with respect to t. So we will have e to the k over mt times v is equal to m times g over k times e to the k over m times t plus our constant of integration. Now, we want to isolate v, so if we multiply both sides by e to the negative k over m times t, then we will have v isolated on the left, and then we will just have m times g over k for the first term, and then c times e to the negative k over m times t for our second term. All right, so now we want to find c. So remember that v at 0 is equal to v0. So v0, our initial velocity, would occur when we're at time t. So we'd have mg over k plus c e to the negative k over m times 0. And that will give us v0 is just equal to m times g over k plus c. Good so far? All right, beautiful. So one more little thing. Let's go ahead and isolate c, and we'll have v sub 0 minus m times g over k is our c. And then I'll write it here at the top of this next page. We will have v at t is equal to m times g over k. Now I'm going to put that big c in, and that was v sub 0 minus m times g over k times e to the negative k over m times t. So I'm just taking this c from here and plugging it in here. And we have our general formula. Okay, so use this solution to determine the limiting or terminal velocity of the mass. So all you do for this one is you find the limit as t approaches infinity of your function. So in this case, it's all this good stuff, mg over k plus quantity v sub 0 minus m times g over k times e to the negative k over m times t. And remember, the limit of a sum is the sum of the limits. And so the mg over k is just a constant. All right, so you'll get the constant. The limit of a constant is the constant. And then the other stuff, what will happen is as t goes to 0, that whole term goes to 0 because your denominator would be, if you wrote it as either the positive k over mt, it would be getting very, very large. So it would be plus 0, which is just m times g over k. Cool, cool? All right, so now getting a little mathy again. If the distance s measured from the point where the mass was released above ground is related to velocity v by ds dt equals v at t, find an explicit expression for s at t if s at 0 is 0. So we have this initial condition, but we can only use it when we find s. So we have to work with, so we're working with ds dt equals to v at t, and then we're working with our initial condition s at 0 is 0. So we know the velocity, right? So ds dt is equal to m times g over k. So I'm looking at this one at the top of the page now, and that's plus v0, minus m times g over k times e to the negative k over m times t. And now I need to look at this. I know it looks ugly, but believe it or not, it is separable. There's no s's on the right side. So here, if I multiply both sides by dt, I'll get ds is equal to m times g over k plus v0 minus m times g over k e to the negative k over mt dt. All right, so integrating both sides of this, a couple things going on. So I'll have s on the left side, and then this first term will be m times g over k times t. Now I will have v0 minus m times g over k is just going along for the ride. But notice I need a factor of negative k over m from the exponent. If I did a u substitution, I would say u equals negative k over mt. So I need, for that portion of the integral, a factor of negative k over m with that dt, right? And so I need to multiply on the outside by negative m over k. So I'm multiplying by negative k over m, but I need that to be 1. So I will have I'll make this minus m over k. The other stuff went along for the ride, and then my exponential was all set up, so I'll have e to the negative k over mt plus our constant of integration. All right, so now we will use our initial condition. So using our initial condition, we will have s at 0 is equal to 0. So 0 would equal to m times g over k times 0 minus m over k times v0 minus m times g over k e to the negative k over m times 0 plus c. So I'll have 0 equals 0 minus m over k times v0 minus mg over k. E to the 0 is just 1, and then I'll have plus c. So then positive m over k times v0 minus m times g over k is equal to c. So, not a really simple looking formula, but at the end of the day, s at t is equal to m times g over k times t minus m over k times the quantity v0 minus m times g over k times e to the negative k over m times t plus c, which is m over k times v0 minus m times g over k. And that was from plugging in what we found for c into our s equation. And that's what we get. All right, awesome. Well, we sure explored lots of fun linear models and differential equations. So I hope you're having a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, hit that like button and subscribe. Bye.